Thank you for introduction, Mr. Chairman. Ladies and gentlemen, I'm with the Institute for Microelectronics and Microsensors at the University of Linz in Austria. And we are inter alia dedicated to research on miniaturized sensors and sensor systems, mainly for fluid properties. And in this context, we're also doing some research on microfluidic components. So I will start my talk with a short outline. First of all, the idea for this work, then briefly the device concept and the working principle. Then I will describe in short the fabrication technology, followed by some measurements with the functional prototype, and I will end my talk with the conclusion. So the idea for this work is actually the realization of a simple device for simultaneous pumping and microfiltration in microfluidic test setups. And the idea is to utilize the well-known nozzle-diffuser approach with an actuating membrane. The sketch on the right-hand side shows the principal configuration for a nozzle-diffuser pump. It essentially consists of an actuated membrane which induces pressure strokes on a confined fluid volume. And due to the asymmetry in the geometrical configuration of the channel underneath, which also induces an asymmetry in the hydrodynamic resistance, a unidirectional fluid flow evolves. Well, and what we did is we integrated this nozzle-diffuser approach directly into the actuated membrane. And the second thing is we tried to design an open-porous foam, which essentially represents a filter structure in such a way that it can act as a nozzle-diffuser structure. This looks strange at the first glance, but will become clearer in the next slides. So here's a sketch of our device. In the middle, there we have this open-porous foam, which features a gradient in the pore size. So from left to right, the pore size becomes bigger. And we additionally have a ring-shaped magnet for electromagnetic actuation, which is also integrated into this PDMS membrane. So how does this work? This membrane integrated into the middle of an symmetric fluid cavity and externally actuated with an electromagnetic coil, which induces an vibrational motion of the membrane. And due to the asymmetry in the hydrodynamic resistance, due to the foam structure, unidirectional fluid flow is expected to evolve. Now some words concerning the fabrication technology. We used the PDMS technology because it's easily controllable without cost-intensive equipment, at least at the lab scale. And it has several advantages for microfluidics. It's optically transparent, it's flexible but mechanically strong, and it's biocompatible, and it can be combined with a large variety of other materials. We used the sill guard from Dow Corning, and the fabrication of the open-porous foam was done with a modified so-called salt method. In using this salt method, sodium chloride grains are used. We have used sodium chloride grains with a defined size, realized by grinding and sieving this salt, so that we finally got grains in the size range between 1 and 50 microns, then 50 microns to 250, and 250 to 500 microns. So and these salt grains were then interspersed in layers into a casting mold and slightly squeezed with manual pressure. Then the whole thing, the PDMS was applied, and it was then cured at a slightly elevated temperature. The picture here on the right-hand side shows a photograph of this cured PDMS matrix with the sodium chloride grains and with the large grains on top and the very small grains at the bottom. So the whole thing then is put into water to dissolve the sodium chloride grains, which finally then leaves the open porous form structure with the big cells at the top and the very small cells in the order of 1 micron at the bottom. The actuated membrane itself is realized with a standard casting process with PDMS, leaving the central part open for the actuating magnet and the form structure, and in the final assembly step, membrane, ring magnet, and the form put together with an adhesive bonding step. The picture on the right-hand side shows a close-up view of the center part of the membrane. Well, already have reached the experimental setup. The picture shows the test setup. The red thing here is the actuation coil. Here is the housing with the integrated membrane. As a housing, we just use the standard syringe filter holder. The fluid reservoir is connected to the diffuser side of the setup. Diffuser side is the side with the big cells in the open porous form. And then a frequency sweep was performed, and between 1 Hertz and 10 kilohertz. And the flow rate was measured with a microbalance. So here the experimental results with first functional prototype. Here in this graph, the flow rate in microliters per minute is shown as a function of the actuation frequency. And the membrane exhibits, as expected, resonance characteristics with a sharp resonance at about 150 Hertz. The relatively low flow rate in the order of 1 microliter per minute is due to the high hydrodynamic resistance of the form structure and the limited output power of the function generator. The driving voltage here was roughly 300 millivolts peak. So in order to test the capability for microfiltration, we also applied some model suspensions to the device with particles in size distinctly below the smallest pore size, which is 1 micron, and above we used polystyrene particles with 11 micrometer diameter, and we dispensed this model suspension into the diffuser side of the fluid cavity. This means into the fluid reservoir. Then we operated the pump for about 30 minutes, and after that we took some samples at the diffuser and at the nozzle side, and one can see that at the nozzle side just the blue ink managed to pass through the membrane. At the diffuser side there's still the suspension with the big particles. So I've already reached the conclusion. I've shown that a modified nozzle diffuser pump concept where an open porous form structure with a gradient in pore size is directly integrated into the actuating membrane. The device can be used for simultaneous pumping and microfiltration, and a quite important point, due to the vibrational motion of the membrane, it is expected that fouling and clocking effects can be suppressed. And the next steps which we want to do now is the optimization of the pumping and filtration efficiency. One major point is the form technology, so we just use the very simple and approach for the realization of the form structure, which is, on the other hand, not well defined. And a minor technology issue is the realization of the whole device in polymer composite technology. The actuating magnet is still a commercial neodymium magnet, and in a former work we have shown that with a composite of PDMS and neodymium powder we can realize quite strong permanent magnets. So thank you for your attention.